Good afternoon, everybody. Thank you for lobbying online this afternoon. Tomorrow it's a very exciting day for us in Cape Town. It's the winter solstice, so tomorrow is our longest night, and after that, we're heading back for summer, and hopefully all of these Cape storms that we are experiencing are going to start slowing down. So for me, the 21st of June is always a nice day because it marks in the middle of winter. But that's not what we're here to talk about today. We're here to talk about this very controversial subject of why you cannot regrade EN10025JR material to J2 material and what the metallurgy is around that and the consequences of doing so. I just wanted to give some background as to my experience as a metallurgist, because it does talk to some of the key metallurgical issues around the regrading and why you cannot regrade JR material to J2 material. So I started metallurgical engineering in 1992 at the University of Cape Town, when materials engineering was still a degree program at the University of Cape Town. Sadly, that's no longer the case. And I went on to start a master's degree where I was involved in an alloy development project called chromonite. So off the back of the success of 3CR12, which was developed by Columbus Stainless in South Africa, they started to venture into high nitrogen stainless steels because of the increased pressure on the nickel price and trying to find another way to achieve an austenitic stainless steel without the addition of nickel. And they very successfully developed an alloy called chromonite with no nickel and fairly high levels, relatively high levels of nitrogen. And when I say high, that's between 0.5 and 1% nitrogen. And that amount of nitrogen was sufficient to be an austenite former and create austenitic stainless steel with superior corrosion resistance and mechanical properties. So my project during my master's, which I later upgraded to a PhD, was to characterize the 1% high nitrogen stainless steel chromonite, which was intended for casting applications. And those were for lifting bars in molds and liners for ore chutes and so on. So it has superior corrosion resistance and superior abrasion resistance. And what Columbus wanted to know was what would happen if we added niobium and vanadium to this mix, and could we introduce precipitates or particles into the steel very much the way high-strength alloy steels are designed today. So that was the thinking. I characterized an alloy from its solidification process all the way through to the various heat treatments that could be applied to the chromonite, and optimized the alloy design and heat treatment for corrosion resistance and wear performance. Sadly, during my write-up, in December of the year that I was meant to hand in, Columbus was bought out by Ceranox and they discontinued chromonite. So they said, really fantastic piece of work, amazing innovation, but unfortunately it's not going to be commercialized. But the silver lining was that I was part of the community of high nitrogen stainless steel development, which led to the commercialization of duplex stainless steels. And people don't always know that duplex stainless steel relies on between 0.2 and 0.4 weight% nitrogen to achieve the duplex structure. So it is an alloy of nitrogen, which many people don't know. So that's my background in alloy development. And then after I finished my PhD, and this is also relevant to the talk today, is I worked on programs on optimizing the hot rolling schedules of aluminium, carbon steel, and austenitic stainless steel. So my projects, which I ran through various master's and PhD students, as well as my own projects as a postdoctoral fellow for 2 years, was to help those 3 steel mills, Saldanha Steel, Columbus Stainless, and Hulamin, in optimizing a hot rolling schedule. So in other words, the temperature at which they roll and the amount of strain that they apply during each pass during rolling. And we're going to see a video of hot rolling later. So that the materials would have the best mechanical properties and And the thermomechanical processing applied to these materials would give them the best combination of mechanical properties. And so both foundry technology and hot rolling schedules and thermomechanical processing are the key points as to why you cannot regrade JR to J2. So we go into the next slide. Jack and Rose could have lived happily ever after if the Titanic had not sat. So let's have the audio visuals, not too loud. And as we kind of get our heads into this presentation this afternoon, I'm going to read to you some metrics that are pretty scary and what I believe is critical to why we find ourselves in this position where we think it's okay to regrade materials. So in the United States today, there are 420 materials engineering consulting companies that employ between 100 and 1,000 people. There are 230 that employ between 5 and 100 people. That means there's about between 400,000, 24,000 employees in the materials engineering space. So let's kind of level that over to around 200,000. And let's say 70% of those are actually hits. Just some other metrics. In the USA, 86 million tons of steel is used each year. Today in Africa, we consume 25 million tons annually, which is about 30% of what America consumes. But in the USA, there are 200,000 metallurgists. And in South Africa, we don't have the same ratio of metallurgists helping these problems. All right. So in order to understand this, I'm just going to touch a little bit on what is metallurgy. And when I studied metallurgy, there was this famous metallurgist named Mike Ashby, and he became knighted for his knowledge in metallurgical engineering and how he educated people in the field of metallurgical engineering. And he put forward this concept of the relationship between the material's microstructure. So we'll look at what microstructure is in a moment. And that the microstructure is a direct result of how it's been processed, which gives the material its properties and dictates its performance. So those four things are all linked together. And that's essentially what you spent 4 years studying, okay? Is this relationship between the performance of materials, their structure, how they're processed, and their properties. So what is a Charpy impact test? The traditional thing that happens in the industry is we buy in 10025 JR material, we conduct a set of Charpy impact tests. They happen to pass the 27 joule requirement at -20 on this machine. And here you can see a little sample of a Charpy impact test specimen, very nicely machined to tolerance with a notch in it. And on the right-hand side, you can see the Charpy impact testing device, which is the one that we had downstairs. And basically this hammer at the top that you can see on the right-hand side is released. It moves through, it whacks the sample is notched, and it measures the amount of joules required to break the sample in half. And that is essentially what the Charpy impact test is all about. And this test is conducted against ASTM E23. Now, why was this test invented? Why was it even developed? Why is it even important? Well, it comes back down to why did the Titanic sink? And the reason the Titanic sank is that in the olden days of steel making, it wasn't known that steel, in the way that it was manufactured in those days, under static conditions, a normal tensile test, in those days done on a Tinnis-Olsen tensile testing machine, they were able to measure the force at which the material would fail. But that was a relatively static test. Nobody applied their mind to the possibility of what would happen to steel when it got to a low temperature. And it was actually the root cause analysis investigation of why the Titanic sank that led to the analysis of the steel that was used to build the Titanic, which led to the finding that steel is a material that actually transforms from ductile to brittle at a particular temperature. And this is called the Charpy shelf temperature. So on this graph, you have on the y-axis, notch impact energy, and on the x-axis, temperature. And in this case, the temperature goes from on the right-hand side to, say, room temperature or higher, and towards the center of the graph, or the intercept between temperature and notch energy, you have lower temperatures of, say, -20, -40, -80. And this is a material where at room temperature, so this would be a typical JR type material, where you would measure its impact energy, and it would be over 27 joules at room temperature. And as you cooled the material down at around 0 degrees, -10, the Charpy impact energy that you would measure on that machine would drop, and then it would reach its lower shelf energy, where it wouldn't decrease any further, even if you cooled it down more. But this property that steel has, which is a characteristic only of mild steel and cast iron, was not known at the time of building the Titanic. So when the Titanic hit the iceberg, the steel was at 0 degrees. It was subject to a high strain rate event, and it fractured. And that's why the Titanic broke in half and sank. Only steel behaves in this way, which is an important thing to remember. Copper, aluminium, and austenitic stainless steels do not. And the reason for that is that these materials, copper, aluminium, and austenitic stainless steels, have what we call a face-centered cubic structure. The atoms are arranged in what we call a face-centered cubic structure in metallurgy, and carbon steel is arranged in the body-centered cubic structure. And it's, in fact, the way in which the atoms are arranged that make it susceptible to this behavior. And so that's why you also have some of this behavior with duplex stainless steels, because you don't only have austenite, you have an austenite-ferrite phase balance. And that is why Charpies are required for weld procedure qualifications for duplex stainless steels, because of this problem in the ferrite phase. But what's important to understand for today's lecture is that it is only really carbon steel that behaves like this. And modern methods of steel making have moved this temperature at which it transforms from ductile to brittle. So the ductile to brittle transition temperature, modern methods of steel making have moved that temperature to lower temperatures. And that's why you can even build cryogenic chambers that can carry liquid nitrogen, because of the way in which the steel is made. Its ductile to brittle transition temperature is being reduced to very, very low temperatures. So it's still ductile at those low temperatures because of the way the steel is made. So why does this matter? Structural steels like JR and J2 have different properties and are used for different applications. That's why they are scheduled in EN 10025 as two different materials. And in fact, JO is also in part of this family, and EH36 is also in this family of 10025. And these are all 4 different materials manufactured in 4 different ways. The J2 material is specifically designed for low temperature impact toughness. But what we see in the industry is that some fabricators attempt to use JR material for J2 applications by simply buying some JR material, conducting a set of Charpy impact tests, and if they happen to pass the J2 requirement, miraculously the material is transformed into J2 material, which cannot be the case. What's even more disturbing is that sometimes the Charpy impact tests are done 4 or 5 times before a set is passed, and the fail tests are ignored. It's only the pass test certificate that's put in the dossier, and we magically have J2 material. Yeah, so I think that in itself is evidence that this really cannot work. It's nonsensical. But I'm going to explain to you the metallurgical reasons why. So it's tied up in 2 things. This impact toughness of 27 joules at 20 degrees and at -20 degrees is tied up in the melting process and the hot rolling process. In the melting process, it is the deoxidation process that is used when they are melting the steel and melting the ore, as well as the control of the amounts of inclusions, which is kind of related to the deoxidation process. With the hot rolling process, the grain structure, JR has coarser grains compared to J2, and JR has what we call crystallographic texture, which I'm going to explain in detail, which is different to J2 material. And that is tied up in how the material is hot rolled, the temperature at which it is hot rolled, the speed at which it is hot rolled, and how much reduction in gauge is applied to the steel as it goes through each pass during hot rolling. So there's a very different recipe in hot rolling schedule, that's what it's called, for JR material compared to J2 material. And there's a very different way which deoxidation and inclusion control is managed for JR and J2 material. So breaking it down again, just a bit of repetition to make the points. The J2 material is a deoxidation process is applied, which is termed a fully killed steel. I'm going to go into what that means. The JR material is semi-killed. We're going to go into what that means. There are tighter restrictions on inclusion content in JR2 material, less restrictions in JR material. Hot rolling schedule is controlled. For J2, hot rolling schedule happens much faster, which is why the steel is much cheaper. First of all, the deoxidation process is not as tightly controlled, and secondly, the hot rolling process is much faster for JR material than it is for J2 material. Okay, so just understanding a little bit about deoxidation. I don't know how many people have been to a steel mill. I've spent quite a bit of time at Saldanha Steel when it was still around, and it always impressed me to see the steel being poured and continuously cast to make the roughing slab. Deoxidation is a process whereby the oxygen is removed from the molten steel to prevent oxide formation. So if you can imagine this big melt pot where they put a bunch of electrodes in to arc the ore and get it to melt, and you consume an enormous amounts of electricity, this process happens under air. So it's very easy for oxygen to be drawn into the steel. And so the steel is covered with something called cover fluxes, and that prevents the oxygen from diffusing into the molten steel. And the cover fluxes also help control the alloy chemistry. So things like manganese have to be added to the steel. And in order for the manganese, because all these elements melt and vaporize at different temperatures, cover fluxes are put on top of the steel to control how it responds to the environment. So if oxygen is taken into the steel during the melting process, it will lead to defects, reducing the steel's strength and its toughness and its weldability. And so deoxidizers like aluminum oxide, silicon oxide, and other calcium products are used as cover fluxes to prevent this from happening. In the case of rimmed steels, which you might have come across, the steel is made under a vacuum. That's not the case in the EN10025, where there has to be quite a lot of slag control. So the stuff that sits on top of the steel has to be scraped off before it's poured into the continuous caster. So a fully killed steel means that the steel has been completely deoxidized before casting, using things like alumina, silica, and calcium-based products. And this is key to producing J2 and EN36. A semi-killed steel means that it has been partially deoxidized before casting. So some oxygen does remain in the melts. In other words, oxygen actually is in solid solution in the steel. And also inclusions such as aluminum oxide and silicon oxide are present in the steel. And this is what oxide inclusions and manganese sulfide inclusions look like under the microscope. So if you look at the image on the left-hand side, this would be considered a very dirty steel. Just definitely not what you want to see. In fact, we have a mass at the moment of fast brittle fractured components, a large tonnage of them. And this is what they look like. And this is pretty much the reason why they failed catastrophically. So these oxide inclusions are very bad news for Charpy impact toughness and increasing the shelf temperature and the ductile to brittle transition temperature to higher temperatures. Okay, so JR and J2 are not the same material since they are not given the same deoxidation treatment during casting. That's a simple conclusion that we can draw there. All right, so introducing a hot rolling process. A hot rolling process takes a continuously cast slab and systematically reducing its thickness step by step to create a thin strip or plate. And I think since the YouTube video didn't work with, you couldn't get my voice while we were playing the YouTube video, I'm not going to play it. Yeah. Okay. The slides will be distributed to everybody that participated in this call. So you can have a look at the YouTube video. I still find it really impressive, which shows how geeky I am. To see a rough slab that's probably about 500 millimeters thick or more, be rough rolled, and then eventually the steel gets longer and longer and longer, and so it has to be made up into these coils, and it goes through a press, and that reduction in thickness, the applied strain causes the steel to lengthen. So if anybody's ever made pasta before, it's exactly the same process. So if you want to know how steel is rolled, just make some pasta and you'll get to learn how steel is rolled. Okay, so the process of hot rolling is either reheating a slab, or if it's not continually cast, rough rolling until such time as it becomes so long that you can't manage this very long piece of steel. So you have to start coiling it. Then finish rolling it to the final thickness and shape. Controlled cooling, air cooling or accelerated cooling, especially in the case of J2 material. And then cutting and inspection and sizing and quality control. So the key parameters in rough rolling for J2, it's not on here, sorry. The rough rolling happens at a higher temperature than the JR material. J2 is finished at a lower temperature, which means that the whole process takes a little bit longer because the strain that's applied during each pass, they're not able to apply the same amount of reduction in thickness because the material is not running as hot as when they produce JR material. So obviously the material is hotter, you can put more strain into it with each pass without the coil fracturing. Will be the last thing you want is for that coil to fracture in half, because then you're just going to take it off, throw it away and remelt it and start again. So they have to, because they are rolling at a lower temperature for better grain structure and microstructure, and therefore better impact strength, the whole process takes a longer period of time because they're not able to put in the same amount of strain during each pass as they are when they roll JR material. So the speed of the process in reducing the thickness during each pass, JR is a faster process than J2. The cooling rate for J2 material is also accelerated to refine the grains and to also randomize the texture. And I'll come back to what textures are. But looking under a light microscope, you can see the top image is JR material and the bottom image is typically J2 material. And you can clearly see the difference in microstructure between the two materials. So for those of you who are not metallurgists today, this is the sort of image that you get under a light microscope after mounting a sample in resin, grinding, polishing down to 0.25 microns, and etching it with some nitric acid. And it brings out what we call the microstructure, which I suppose we could compare to a person's fingerprint. It's what the material looks like under the microscope. And how that material looks under the microscope, you can see in the top image, you can see the grains are much larger in comparison to the bottom image. And that grain size difference, just that grain size difference, makes a huge difference to the mechanical properties. But this is just what you can see with a light microscope. And there's way much more than this. And this is the key issue in the development of steel over the years, in that even looking at steel under a microscope was something that only happened in the early 1900s. And interpreting these microstructures and understanding the relationship between microstructure and mechanical properties is what developed during the 1900s. And that understanding led to better steelmaking practices, so that we're not sitting with the same problem of the steel that was used to build the Titanic today. So going back to structure, processing, properties, and performance, there's a lot more that we can see nowadays in the structure of engineering materials by way of electron microscopy. So the electron microscope can actually show us things about the material by using an electron beam to analyze the material. One of these things is the so-called crystallographic texture development. And that is measured by way of electron backscatter diffraction. So if you're geeky metallurgist like me, I spent a lot of time on a transmission electron microscope during my PhD, characterizing various phases in my chromonite material. And you see these so-called Kikuchi bands in the image on the left-hand side. And these Kikuchi bands guide you to certain crystallographic positions where you can then get a diffraction pattern, and that diffraction pattern can be used to tell you what the crystal structure is of a particular phase that you are looking at. So they're like a map. But during the time of my PhD, electron backscatter diffraction as a method became widely used throughout the world to measure the crystallographic orientation of hot-rolled products, because it was found that in some hot-rolled products, there would be a preferred crystallographic orientation of the grains, and in others, it could be completely random. And what's important to point out is that because J2 is a control rolled, the texture that develops is much more random, which reduces the Charpy shell temperature. So it's actually this orientation of the grains and how the atoms orientate themselves during hot rolling that contributes towards the Charpy V-notch energy. The JR material has less controls, which gives it a preferred orientation, which is not what you want in terms of mechanical properties. But what does this look like? All right, so this is essentially the setup inside the electron microscope. You have an electron beam, hits the sample at a certain angle, and you have a special detector that measures the diffraction patterns in the form of Kikuchi lines that you're seeing there. And those are analyzed by way of computers. In my day, when I had to do transmission electron microscopy, it was all done by hand, and I had to develop my slides myself in the darkroom. Today, you have computers that can read those Kikuchi patterns and orientate the sample and tell you exactly what crystal structure you're looking at. It's really irritating because I could have done my PhD in a year if I had that technology. But what this generates is a map of the microstructure. And so similar colors mean similar orientation. And I think what's also important about this image is this is a typical JR material. And what you can see here is you can see that the grain structure is finer on the surface than in the center. So this is the reason why sometimes the Charpy test actually passes the J2 requirement. But that might be because you've taken the Charpies out of the skin and not out of the center of the material. The next time you do the Charpies, maybe you take one out of the center, one out of the skin, and one out of the other skin. And so 2 pass and 1 fail. And that's because of the variable nature of the microstructure and the crystallographic texture of the steel as a result of the way it's hot rolled. This is what a J2 material looks like. So you can see this is exactly what you want. It looks like a church window, stained glass window, because it's a beautifully clean, highly random texture orientation. And the more random the texture is, the better mechanical properties you have and the more reliable the mechanical properties are. But I do want to point out with this image that the reason why you can sometimes get lucky and get JR to pass is because along the length of that coil, which you saw how long it was, and across the width and through the thickness, you can get such a huge variation in Charpy energy, whereas you get much more consistent results with a J2 material. And so trusting one test result to qualify a whole heat, in other words, a whole coil, is a very dangerous practice indeed. But to summarize, JR material is hot rolled above the recrystallization temperature. Recrystallization is the temperature at which, when you deform the grains, they reform again, and therefore would give a bit more resistance to the hot rolling process. They finish it at a relatively higher temperature so that they can put more strain in per pass and roll the coil a lot faster, which results in a coarser grain structure and a preferred crystallographic orientation. J2 is hot rolled at lower temperatures than 900 degrees. And due to the strain accumulation because of the lower temperature rolling, you need a longer processing time, but this does result in finer ferritical-like grain structure and a random crystallographic orientation. So you can see here how the structure and the way in which you process gives you certain mechanical properties that affect the performance of the fabricated item. So in summary, JR material is a totally different material to J2 and EH36. The key differences are in the melting procedure and the hot rolling schedule. This ties together with process, structure, properties, and performance. JR cannot reliably deliver on Charpy beam-notch energy at -20. If you have a test result that gives you that, you were really lucky. But how many times has it failed 5 times before you got a result that passed? J2 is designed to be reliable and deliver Charpy beam-notch energy at -20. So JR has its place, fitness for purpose, structural applications, bridges and beams that are not exposed to cold temperatures, whereas J2 is used for low temperature environments, offshore structures, subsea fabrication. The surface of the temperature of the water is not the same when you're going to do deep drilling. And that's very concerning if people are regrading JR to J2 for subsea fabrication when the temperature of the water at maybe 200 meters is going to be very different to the surface temperature. And this is definitely not what we want. What is the cost of reputation? It's very difficult to quantify the cost of your reputation. And certainly the CEO of BP suffered tremendous reputational damage. This was a record-setting in penalties. BP paid the largest environmental criminal fine in US history of $4 billion US, and the largest civil environmental settlement ever of $20.8 billion US. And I think that just want to leave you with a message today that there is a reason why the code talks about these two different materials as two separate materials. And it's to prevent these kind of catastrophic failures from occurring. And I think that unless we apply ourselves and accept what the metallurgists have to say, placing yourself at great risk. Thank you. Questions from the audience?
Hi, Janet, can you hear me?
Yes, John.
Sorry, it's Zander speaking.
Oh, Zander. Yes, hi, Zander. We can hear you. It's a bit slow.
Okay, is it better now? Just a question from my side is, a lot of the times we, from our fabricators, we hear that they cannot obtain J2. So we have had these requests there where they want to test the JR to J2 material. If there is not a J2 available, what other material can you recommend that is similar in capacity to J2?
Well, I struggle to understand why J2 is not available because I know Charles Camel very well, who used to be the CEO of Max Steel. And I've actually, when he was still the CEO, I introduced him to a few of the fabricators in Cape Town, and he said, contact me directly. I will find J2 material for you. So that he doesn't, in his experience of 30 years of being a steel trader, doesn't understand that problem at all. He believes that it is available. And certainly my experience with my clients in oil and gas outside of South Africa, they don't have any problem sourcing J2 material. So,
Is that only in plate material? Because normally we struggle with sectional steels like I-beams and H-beams.
Well, yeah, once again, I've taken Charles on a sort of field trip around to various fabricators, and he's unequivocally said that he doesn't believe that it's not available. It's just too easy to buy JR material, which is cheaper, and do a set of impact tests, um, in many cases at an unaccredited lab, and transform it by way of paperwork into J2 material. I think it's just become a habit. And because it's become a habit, it's become accepted. Everybody does it, so it must be acceptable, right?
Okay.
Nice. Yeah.
Thank you very much.
Okay, John, you have a question.
Not a question, China, just an observation or some comments on J2 and J0 material or JR material. People regrade JR to J2 and then they weld on it, which makes it even worse because they've got qualified procedures for J2, but they don't understand with the grain growth issues in the heat affected zone, which will destroy all of the impact properties that they thought they had. Where they barely maybe passed with the JR material now, in practice, they will not achieve that, and then they will have early failures and cracking and all kinds of things happening to the structures, not understanding why.
Yes, thank you for that comment, John. I think that's very important. So you're saying people have qualified welding procedures for J2 material, they buy JR, convert it by way of Charpies, and then can't understand why the essential variables don't work. Rob Lawrence, do you want to comment on that?
Yes, a little bit. I mean, it is susceptible to hydrogen cracking, but the problem is exactly what you said. People don't know the difference between, or John has just said, they don't know the difference in the the metallurgical side of the two different materials, and they've got a procedure for one, but they'll weld it the same way. If you don't use low hydrogen electrodes when you're welding and into heat input, if you don't do this properly, you will definitely get into granular cracking. It's it's all about education, and you've just explained the right difference between the two materials. And we know Charles loves that material, but if it's not available, the problem is exactly what John has said: using the wrong welding procedure or using the wrong material with the welding procedure. It's education.
Thanks, Rob. Pamoin, you have your hand up?
I'm unmuted. Yes, I'm here. Hi everybody. My question was just if whether or not, Janet, you're seeing an increase in these kind of requests to regrade JR to J2, but I think your comments that it is kind of becoming the norm. It answers the question, I think.
Yeah, so we've taken a position, Hamoin, in our laboratory that we refuse to do the test for this purpose. Even if people request for us to do Sharpies on JR material, I will ask them, why are you just this out? And if they tell me they're wanting to regrade the material, we as a company and as a brand and me as a professional want nothing to do with it. I don't want my name attached to it. In my early days of running the laboratory, I was perhaps a bit naive and didn't understand. But now, 12 years later, it's not something we're prepared to do at all. And I believe the only way that we're going to facilitate change within our country and facilitate the education and understanding of metallurgical engineering is to take such strong positions on the matter and other matters as well that's related to metallurgical engineering.
No, absolutely, and therefore thank you for this presentation.
Thank you for mine. Always good to have you. Any other questions? Okay, well, I think that concludes our presentation for today. Thank you, everybody, for participating at short notice. The slides will be sent out to you together with a technical bulletin that I've published on the matter. And the video will be available shortly, I suppose within a week or two, on our website. So please don't further and ask why you can't regrade JR to J2. Just watch the video again, or read the dossier, or look at the slides. That's why I'm giving this presentation today, because I'm tired of repeating myself. Thank you very much, everyone.
Thinking. Keep off the Titanic.
Yeah, let's move on from the Titanic, guys.